Mechanical properties of concrete in civil engineering. Today, we will explore the fundamental mechanical properties that determine how concrete behaves under various loading conditions and environmental factors. Understanding the mechanical properties of concrete is crucial for structural engineers. These properties determine how concrete structures respond to loads, environmental conditions, and the passage of time. Engineers must consider compressive strength, tensile strength, elasticity, time-dependent behaviors like creep and shrinkage, and long-term durability. Let's examine each property in detail. Compressive strength is concrete's most important mechanical property. It measures the maximum compressive stress concrete can withstand before failure. Engineers test compressive strength using cylindrical or cubic specimens at 28 days after casting. Typical concrete has a compressive strength between 20 and 40 megapascals, while high-strength concrete can exceed 100 megapascals. This property is denoted by F'C or FCK in design calculations. Concrete's exceptional compressive strength makes it ideal for columns, foundations, and load-bearing structures. Tensile strength is concrete's major weakness. When subjected to tension, concrete can only withstand about 10% of its compressive strength, typically between 2 and 5 megapascals. This low tensile strength means concrete cracks easily when pulled or bent. The relationship between tensile and compressive strength is expressed as tensile strength equals approximately 1/10 of the compressive strength. This fundamental weakness is why engineers use steel reinforcement in concrete structures. The steel bars carry tensile forces while concrete handles compression, creating an optimal composite material. The modulus of elasticity, also called Young's modulus, measures concrete's stiffness or resistance to deformation. It is defined as the ratio of stress to strain in the elastic range. For concrete, the modulus of elasticity is approximately 4,700 times the square root of the compressive strength. Typical values range from 25 to 35 gigapascals for normal concrete, and 35 to 45 gigapascals for high-strength concrete. This property is crucial for calculating deflections in beams and slabs. The stress-strain relationship shows how concrete behaves under increasing load. Initially, concrete behaves almost linearly in the elastic region where deformations are recoverable. As stress increases, the curve becomes non-linear due to microcracking. Peak strength occurs at a strain of about 0.2%. After the peak, concrete shows strain softening behavior, meaning it can still carry load but at reduced capacity. Unlike steel, concrete exhibits brittle failure with no yield plateau, and the ultimate strain before crushing is typically around 0.35%. Creep is the time-dependent deformation of concrete under sustained load. Even when the load remains constant, concrete continues to deform slowly over months and years. This progressive deformation can double the initial elastic deflection. Creep depends on several factors including concrete composition, humidity levels, and loading age. Most creep occurs in the first year, but continues at a decreasing rate for many years. Engineers must account for creep when designing long-span structures to prevent excessive deflections over the structure's lifetime. Shrinkage is the volume reduction that occurs as concrete loses moisture. There are two main types. Plastic shrinkage occurs in the first 24 hours before hardening, while drying shrinkage continues for months as water evaporates from the hardened concrete. Typical shrinkage ranges from 0.02 to 0.06% of the original length. When concrete is restrained from shrinking freely, internal stresses develop that can cause cracking. Engineers control shrinkage through proper mix design, curing practices, and the use of control joints or expansion joints to accommodate volume changes. Durability refers to concrete's ability to withstand environmental attacks and maintain its properties over time. Concrete faces numerous threats. Freeze-thaw cycles cause internal pressure and cracking. Chemical attacks from sulfates and chlorides degrade the cement paste. Corrosion of embedded steel reinforcement leads to spalling, and abrasion wears away the surface. Durability depends on several factors including a low water-cement ratio, proper curing, adequate concrete cover over reinforcement, air entrainment for freeze-thaw resistance, and use of quality materials. A dense, impermeable concrete matrix is essential for long-term durability. The mechanical properties of concrete are fundamental to structural engineering. Compressive strength remains the primary design parameter, but tensile strength, modulus of elasticity, stress-strain behavior, creep, shrinkage, and durability all play critical roles in determining structural performance. Time-dependent behaviors like creep and shrinkage must be carefully considered for long-term safety. Understanding these properties enables engineers to design safe, efficient, and durable concrete structures that serve society for decades. Thank you for learning about the mechanical properties of concrete.